Hello, hello everyone. Today my presentation is on our paper, the data-driven forecasting and solution approach for the dial-a-ride problem with time windows. I'm Dr. Salim Belhaiza. I'm from King Fahd University of Petroleum and Minerals. I'm associate professor with the Department of Mathematics. So today's presentation, the content will go through an introduction and the problem description. We'll talk briefly about the literature review, and I will try to describe our neural network forecasting approach. I'll talk about the data-driven heuristic we used and the results and the conclusions. So first of all, for the definition of the problem itself, vehicle routing problems address various aspects of the key economic activities in modern cities economy. And the dial-a-ride problem, in fact, defines a subclass of VRT problems, where we do have an heterogeneous fleet of vehicles, which should be considered to meet customers' needs. And this is mainly due to accessibility restrictions that forbid some vehicles from visiting some locations. The most usual case arises in door-to-door transportation for senior or impaired people. So the objectives and variants of the DART, the aim of the DART is to design a set of minimum cost vehicle routes satisfying all requests and or set of constraints like maximum capacity route, maximum duration, and passenger maximum transit time. Among the extensions of the DART, the cases where services at customers should be within a certain period of time, we define the DART with time windows. We abbreviate it by DARPTW. So the DART is static when all requests are known at the time of the planning. Otherwise, it's called dynamic if requests are received during the execution of primary routing plan. The DART could be described, in fact, as a pickup and delivery problem within windows, maximum duration, maximum transit conditions. The DARPTW could be defined also on a graph, where you have V as the vertices set and A as the axis. The DARPTW contains, in fact, a number of customers, you may call N, and a set of M vehicles. A customer I has, in fact, two different stops, one for the pickup, you may denote as I plus, and one for the drop, we may denote by I minus. So each stop, either pickup or drop, has a negative service time, SI, which is generally assumed to be corresponding or similar at pickups and drops, and two time windows, LI plus, UI plus, and LI minus, UI minus, which represent the lower and upper bounds of the time windows. A pickup stop is generally signaled by a positive event, DI, and the maximum transit time, RI, between the departure from I plus and the arrival at I minus. So a drop stop is generally signaled by a negative demand minus DI, and a vehicle K has a maximum capacity QK, a maximum route duration TK, and work time window LK UK, which means that the execution of the route should be within LK UK. So the DART main goal is to design a set of M vehicle routes on G, such that each route starts and ends at the depot D and satisfies all conditions. Each customer has to be picked up and dropped by the same vehicle within its respective time window, and each route is performed by vehicle K shouldn't exceed the vehicle load capacity and should be within the total duration of within the maximum duration of the route. And of course, we assume here that if a vehicle arrives at the customer before the time window, it should wait. If it arrives at the end of the time window or after the end of the time window, then the route is not feasible. So here I will review some of the innovations of our work. First of all, we propose a data-driven approach to forecast demands, service times, and travel times between nodes. And we study, in fact, different neural network architectures and analyze their performance. So we also propose a data-driven hybrid adaptive heuristic for the DARPTW, and which mainly consists in evolutionary crossover operators with hybridized large neighborhood search algorithm. Data, in fact, is extracted from routes with DARPTW infeasibilities and used to guide customers customized local search operators. And we also conduct some tests on benchmark and real-life instances. So here I will review some of the approaches which exist in the literature. Parag and Schmidt proposed the hybrid large neighborhood search for the DARP with time windows. Matson et al. Proposed an algorithm based on an insertion heuristic. Guerrero et al. Proposed a bi-objective approach. Masson et al. Proposed an adaptive large neighborhood search also for the DARP with predefined transfer points. Among other approaches, you may have the genetic algorithm, taboo search, variable neighborhood search. Likewise, Mahmoudi et al., who proposed a genetic algorithm for the heterogeneous DARP. Cordo et al., Cordo and Laporte, who presented the taboo search heuristic for the DARP with capacity, maximum duration and transit time. As you also proposed the taboo search approach for the dial-a-ride problem. So also we have data-driven approaches, which exist in the literature, among which we may cite Markovich et al., which developed statistical and machine learning models to provide more accurate predictions over a range of scenarios to predict that system capacity. Also, we can cite Florio et al., who focused on the vehicle routing problem with stochastic demands and probabilistic duration conditions. So first of all, we will try to introduce the neural network approach. So mainly, in fact, our DART inputs are referred to as PRTs, while the outputs are referred to as IYTs, and T refers here to the time or observation index. So the activation functions, in fact, tries to approximate the measure of the output at the time or observation index T. And in fact, many ANN activation functions are commonly used, among which we may note the logistic sigmoid function, which is 1 over 1 plus e to the power minus x. So it assumes here that xt is the dot product of the weight vector assigned to the input and the input vector. So the neurons at every layer, L, for a total number of neurons, capital L in our neural network, are dotted with their own activation functions. Here, this is a simplified representation of a neural network. And at the end, the output estimation following one complete forward pass would be the composite function of all the activation functions applied at all the layers of the neural network. And the total estimation error function obtained for each output following one full forward pass through the capital L or the L layers of the ANN is given by the following error function, which is the sum of the square errors. So within a classic steepest descent algorithm, we tend to calibrate or to readjust the weights and the biases using the gradient of the error function with respect to the errors, to the weights and the biases. So in vector form, the classic steepest descent scheme writes as follows. The state of the art in neural network implementation uses, in fact, stochastic gradient descent, ADAMAX, and ADAGRAD. And we can see that stochastic gradient descent is in fact, uses an estimation of the gradient at every iteration, while ADAM is an adaptive moment and estimation, and stores an exponentially decaying average of the past square gradients. ADAMAX, in fact, generalizes ADAM, and ADAGRAD, in fact, is an adaptive gradient algorithm with a modified stochastic gradient descent scheme. So for our dataset contains a huge amount of information collected on a daily basis over a period of 12 consecutive months by 40 vehicles equipped with GPS in Vancouver area. And given that not all edges may have been traversed during the observation period, in fact, we focused on only those who were visited mostly. And the recorded data includes arrival times at customers, waiting, loading times, and unloading service times and travel times on different edges of the Vancouver and suburbs road network. So for instance, here is a representation of one of the main arcs we studied. So from point 0 to point 1, Bird Street to Point Harbour Street, here close to Castellano Beach on Vancouver area, it has been traversed like 430 times during the collection period. So for the input entries, we have longitudes and latitudes for both nodes i's and j's for every arc, the day order of the observation, the season of the observation, the day of the week, and the period of the day. While for the output entries, we have the arrival times, the waiting times, the loading and loading service times, the net demand in the customer of the at the customer, and the measured travel time from on the arc YJ. ij. So the day order is just the order, in fact, of the measurement day in the corresponding year. And we assume that there are 3 seasons in the year, each one lasting like 4 months. And the acquired data in fact, needed to be transformed using some cleansing and completion, because some observation will like containing 0 values. And we had to take like the average travel time in minute per kilometer ratio observed on similar days, similar seasons, similar periods to complete these missing information. So we also use a principal component analysis to remove the features that has no meaning. For example, the longitudes and latitude, like the geocodes of the I's and J's on every arc, were not meaningful. So for instance, we mentioned that the day order has the largest singular value, which is about 1294. And while the other singular values are mostly insignificant for the longitudes and the latitudes. So for the, we also perform the seasonality decomposition, whether additive or multiplicative. We've shown the existence of some particular periodic trend and seasonality component for the travel times, as you may see in this figure. So now we develop, in fact, 2 kinds of architectures. First one has no hidden layer, so which only 2 layers in the neural network, while the other one has a hidden layer. So 2 or 3 layers were used in our current ANN forecast implementation. And the first layer, in fact, was tested using 3 activation functions: logistic sigmoid, the hyperbolic tangent, and a sigmoid linear unit. Where here x corresponds to the dot product of the weight vector by the remaining input we collected from our data. And the number of nodes varied from 5 to 50 for the main layer, for the input layer. For the output layer, it corresponds to the second layer in the 2-layer ANN. And it, in fact, corresponds to the third layer in the 3-layer ANN. And it uses the ReLU activation function, which returns the maximum between 0 and x, and has always 4 neurons. And its main role is to filter any value which may be less than 0. So the hidden layer in the 3-layer ANN, in fact, uses either the log sigmoid or the ReLU function, depending on the first layer activation functions. So about the results, so we tested different gradient optimizers, including SGD, stochastic gradient descent, ADAM, ADAGRAD, and ADAM, and ADAMAX. And the accuracy results are obtained following different numbers of first layer neurons and different activation functions, F1 and F2, on the same arc. And they correspond to the residual mean squared error obtained when the training set size is fixed to 2/3 of the whole data set, and travel times are forecast. So our results correspond to a fixed number of the epochs. And for the main results, so tan hyperbolic activation function provides in general slightly better accuracy than ReLU for 2-layered ANN. The lowest 2-layer ANN RMSE, which is about 0.19, is obtained with S1, which is 5 neurons in the first layer, with the SGD optimizer. And in general, SGD is shown to be slightly more stable than ADAMAX when S varies from 5 to 50 neurons, with F1, which is the tan hyperbolic. For 3-layered ANN, with F1, which is the tan hyperbolic, and F2 with ReLU activation function, we have generally the best accuracy results. And the lowest 3-layered ANN RMSE was about 0.17, and it is obtained with 15 neurons in the first layer, 20 neurons in the second layer, and with the SGD optimizer also. So this is an illustration of the RMSE minimization results of 2-layered ANN, comparing ADAM to SGD optimizer, using the tan hyperbolic and the number of neurons in the first layer, which is 5. You may see here that the SGD tends to be more stable compared to ADAM. And also, this table shows that the SGD in general is more stable, also for 3-layered neural networks, and provides the best accuracy results when used with F1, which is tan hyperbolic, and ReLU, which is F2. Now we'll talk about the data-driven heuristic development in this context. So in fact, DDHLNS operates are based on 4 different kinds of DARP infeasibilities. And the first kind does not involve any route, which is due to customer with both pickup and drops stops left and served. The second type involves a single route where a pickup or drop is found without its corresponding drop or pickup, left and served. And the third kind also involves a single route, but where a drop is found before its corresponding pickup, while the fourth kind involves two different routes found to be sharing a pickup and its corresponding drop. So the main steps of the heuristic, we have a step one, which addresses DARP invisibilities of type 1 and 2. Step two, it applies local search DARP improvement operators, and it addresses DARP invisibilities of type 3 and 4. Step three changes either the center point of the neighborhood of the search and recenters. And step four shakes the current solution using shaking operators. Step five applies a set of randomly chosen solution, a reset procedure based on a randomly chosen solution belonging to a pool of best DARP solutions. Step six applies DARP evolutionary operators to generate new solution. And step seven applies a ruin and recreate DARP procedure. So first of all, the initialization is based on clustering. The construction process generates a random permutation of the pickups and drops of the end customers. And here we do split the whole set of points. So the construction process then sequentially assigns the stops and their order of appearance into cluster radius R. And if you, let's see here the current number of clusters and R the radius of the cluster, construction process sets the focal point of the first pi 1 to 1, for instance. So this is kind of a scheme of construction where there are 4 clusters, and we would for the initialization. Now we will also deal with type 2 invisibilities and type 1 using some insertion. So the insertion phase addresses DARP invisibility of type 1 and type 2, depending on the stops left unassigned. And if the type 2 invisibility corresponds to drop I minus stop left and served, search for the route containing its corresponding pickup, I plus, and tries to insert it. And if the type 2 invisibility corresponds to a pickup, I plus, stop left and served, searches for the route containing its corresponding drop, and tries also to insert it at every possible route where I minus belong. The local search operators defined in the DDHLN steepest descent phase would address the DARP invisibilities of types 3 and 4. It starts from X and returns an improving solution X prime. And it mainly consists in 2 phases. The first phase is a single route DARP improvement phase. The second phase is a multiple route improvement phase. So for the first phase, we apply different single route exchange operators, like the relocate, the swap of positions of arcs or vertices. And this is like a representation of some of the operators used, where we break invisibilities by moving the position of a node or one arc, for instance. And for the second phase, we simultaneously address DARP invisibilities of type 4 while seeking cost-saving stops of or arc exchanges between different routes. So we have inter-route relocate operator moves. The DARP inter-route relocate operator moves one stop from a route and places in a different route. And we have the swap operator exchange, and we have the inter-route cross operator, which moves a selected arc from a route and insert it in a different route. For instance, this is one case where we had some invisibilities before and afterwards. And the invisibility here is due to the fact that you see that I minus doesn't belong to the same route as I plus. So we have to correct this. And now I minus belongs to the same route as I plus. So, and these are other possibilities where the improvement is done. Okay, so there is also a move or not phase where we check out whether we have to set to take this current solution or not. And in fact, it's based on the cost function, which is a weighted sum of the total duration, the violation of the time windows conditions, the overloading of the vehicles, and the non-satisfaction of maximum duration, with some penalties. and it weighs in the fact that we may adopt or not the current solution. We also collect the best genes of the solutions. So in fact, we use a backwards slack time procedure to minimize the waiting time. And the solution characters are regarded as genes. And the most basic representation of a gene here in our DARP implementation is simply the assignment of a stop to a given vehicle. So if the routing solution has exactly the same genes as one of the routing solutions in the best solution pool, the move can only be approved if it improves the overall best solution in terms of cost and number of DARP infeasibilities. So at the end, we have also some restart procedures. So because during the execution of the algorithm, the pool of best solutions is subject to an evolution, and it is maintained in a way such that the newest best solution found takes the place of the oldest. And if some respective conditions are met, 4 different restart strategies are applied, among which the first restart procedure is a regular Venus shaking phase, which allows an alteration of the cost solution and also of the number of DARP infeasibilities. We have other kinds of restart procedures within our algorithm. Finally, we may apply also some genetic crossover operators involving 2 or 3 parents. So about the computational results. So we tested our implementation on DARP benchmark instances proposed by Cordon and Laporte. And these instances involve like from 24 to 144 customers. And the first end stops are the pickups. The last end stops are the corresponding drops by respective index order. And the maximum transit time for each customer is 90 minutes. And each stop has like 10 time units of service time. So the maximum ride duration of each vehicle is about 405 and 80 time units. So the maximum capacity also of each vehicle is about 6 passengers. And the experimental results on also are provided on 10 real-life instances with 30 to 80 requests and 4 to 10 vehicles provided by a company in Vancouver. So it is interesting to note that our algorithm finds routes with a lower number of vehicles and less total duration than the state-of-the-art heuristics. And for example, for instance, PR07 from the Cordon Laporte dataset, the algorithm lowers the total duration by more than 2.5% when 4 vehicles are used, and by more than 0.67% when 3 vehicles are used. And DDHLNS is also able to reduce the total duration on a set of real-life instances by more than 0.46% in general. So some of the conclusions, our findings are justified by the variety of initial solution and restart strategy used with the DDHLNS algorithm. And the classification, in fact, of DARP infeasibilities into 4 different types and the use of data-driven local search approaches adapted to the problem have also certainly contributed to this. And other ANN architecture may be explored in the future to improve the forecasting results. Thank you very much for following. If you have any question, please do.